Welcome back to differential calculus. In this video, our goal is very specific. We want to be able to differentiate an exponential function. Okay, so let's get right down to it. Let's fix a number, a greater than 0. We only ever talk about exponential functions where the base is greater than 0. So we think of a as a fixed number, even though we don't necessarily know what it is. And then we define f of x to be a to the x. Okay, so a could be bigger than 1, less than 1. Doesn't matter. What we care about is that we have a to the x. Okay, so our goal is we want to find a formula for f prime of x. We know what this function looks like, right? A to the x looks something like this. So it should be differentiable, right? The derivative should exist. It doesn't have any corners or anything. So first, let's see what the derivative is just at 0. Okay. So f prime of 0, well, it's defined as a limit. This is the limit as h goes to 0 of a to the h minus a to the 0 divided by h. And what is that? Well, I don't know. I guess we can say a to the 0 equals 1, so it's really the limit as h goes to 0 of a to the h minus 1 over h. Now, what is that limit? Well, it clearly depends on a, or maybe it's not clear, but it does depend on a. And using some really advanced math, you can prove this limit exists for any positive a. Okay, what you do, you don't need to know about this, but you show that this function, a to the h minus 1 over h, is increasing and bounded above, and then a property of the real number says the limit has to exist, even if we don't know what it is. Okay, so this exists, and this limit is f prime of 0. Okay, and just trust me, it does actually exist. So if I want to find f prime of x for any x, that's going to be limit as h goes to 0 of f of x plus h, so that's a to the x plus h, minus f of x, so minus a to the x, divided by h. Okay, now properties of exponents let me split up the a to the x plus h part. So I have limit h goes to 0, and I have a to the x times a to the h minus a to the x times 1 divided by h, and I'm going to factor out an a to the x. So I have limit h goes to 0, a to the x times, and what am I left with? Well, I'm left with a to the h minus 1 over h. Well, that looks familiar. Now, this a to the x here doesn't have anything to do with h. So it's really a constant with respect to h, and that's what's moving when I take the limit. So I can pull it out of the limit. So f prime of x actually equals a to the x times the limit as h goes to 0 of a to the h minus 1 over h. But that is exactly this limit, right? That's the derivative at 0. So what we're seeing is that the derivative at any x is equal to this constant. F prime of 0 is a number. It's not a function or anything. F prime of 0 is just some specific number times a to the x. So this is why exponential functions are so very useful in like science, for example, is because that's how the derivative works. What it says is that the rate of change of the function, that's the derivative, so the rate at which the amount of stuff changes is a constant times the amount of stuff that's there. So if a to the x represents like the population of insects in some forest, then that's saying the growth rate of the population is a number. So this is sometimes called the proportionality constant. We're really saying the two things are proportional. The rate of change, or the growth rate, is proportional to the amount that's already there. So this is really useful for like population modeling. The more insects there are in the population, the faster the population is going to grow. Or it's good for like exponential decay. So like radioactive decay, the more amount of some unstable isotope you have, each molecule has its own probability of decaying, so the more stuff you have, the faster it's going to decay. Okay? So the rate at which the amount changes is proportional to the amount of stuff you already have. So that's kind of what makes the graph look like what it does too. Over here, the function value is very small, so the slope is very small. Over here, the function value is reasonably large, so the slope is reasonably large. Up here, the function value is very big, so the slope is very big, which means it's very steep. And it just keeps getting bigger and bigger as x keeps getting bigger and bigger. Okay? So exponential functions have the property that the rate of change is proportional to the amount present. Very, very useful. That's why they're so good. Okay, so f prime of 0, what do we do about it? Well, that's actually not going to be until the very end. I guess you could skip to the end of the video if you want, but first I want to ask this question. Let's say you're dealing with exponential functions all the time, because maybe you're a scientist or an engineer or something and you like doing math and modeling things. If you had to take lots of derivatives, you're always having a to the x, taking f prime of x, and you got to pick a. So if you got to pick a, remember this f prime of 0 is going to depend on a. What a would you pick? Well, if it was me, I would pick the a so that this number is equal to 1. That way, we would just have that f prime of x equals a to the x without having to multiply by this extra constant every time. Okay? That's kind of the best base. The best a you can pick. It's the best base for any exponential function because it makes the derivative just equal to the function without having to multiply by this extra constant. Okay, so if you got to pick that, you'd probably pick the one that made f prime equal to 1, but how do you know what number that is? Well, that's what we're going to figure out. Okay? So first, let's look at, say, f of x equals 2 to the x. So I'm saying a equals 2 here, and then f prime of 0 would be the limit as h goes to 0 of 2 to the h minus 1 over h. How are we going to find that? Well, let's just approximate it with a calculator. We can certainly get a pretty good approximation by just putting in a small value for h. So let me bring up my trusty calculator here. So what I want to do is I want to approximate this limit by putting in a really small number for h. So let's say this is approximately 2 to the, not to the 0, but maybe to the 0.0001. And then we want to subtract 1. Those parentheses divide by 0.0001. Okay, and we get about 0.693. Okay, so this limit, f prime of 0, is approximately 0.693. That is not equal to 1. Okay, so a equals 2, not the best base. So, for example, if this is our f of x, then f prime of x would be 0.693 times 2 to the x. And that's not really a nice space to deal with, right? Every time you take a derivative, you have to remember to multiply by 0.693. Not ideal. Okay, so what if we try 3 to the x? Well, that seems a little better. F prime of x equals 3 to the x. So let's see. Then f prime of 0 would be the limit h goes to 0 of 3 to the h minus 1 over h, which is approximately 3 to the 0.001 minus 1 over 0.001. So I'm approximating the limit by putting in a small value for h. So let's see what we get if we do that. Maybe we'll get 1. Maybe we'll get lucky, right? So let me just bring that last thing up, and I'll change the 2 to a 3. And, oh, close. 1.1, we'll say, or 1.099. 1.099. So the slope is almost 1 at the origin, but not quite. So what we're seeing is that I have this graph. So 2 to the x grows not too fast. 3 to the x grows faster. The slope here is 0.693. The slope of this one is 1.09. So we see that as a changes between 2 and 3, the functions are going to go from here to here, right? And at some point, the slope right at the origin is going to be equal to 1, because for this, the slope is less than 1. For this one, the slope is greater than 1. So this number that we're searching for is somewhere between 2 and 3. Okay, well, let's pick another one, another base. So suppose a equals 2.7. Why would I pick that? Well, because I know what's coming. So f of x equals 2.7 to the x, and then f prime of 0, we really want it to be 1. Remember, it's the limit as h goes to 0 of 2.7 to the h minus 1 over h. So this is approximately 2.7 to the 0.001 minus 1 over 0.001. And again, we can just ask the calculator, do we think it's going to be 1? Why would I pick 2.7 if it wasn't going to work? Well, let's see. So we have 2.7. Oh, sorry, I have an extra 0 in here. 0.993, and put in an extra 0. 0.993. So the limit is almost 1. Very, very close. So it looks like the best base ever should be close to 2.7. Well, let's try it a little more. Let's try a equals 2.72. Okay, so f prime of 0 for that f of x, 2.72 to the x, would be the limit h goes to 0 of 2.72 to the h minus 1 over h, which is approximately just like before, 2.72 to 0.0001 minus 1 over 0.0001. And here, f prime of 0 is approximately, let's see. So we have 2.72. Now we went a little bit too far, 1.0007. So the best base, A, is in the interval. It's somewhere between, open interval, between 2.7 and 2.72. Now it turns out there is exactly a number that satisfies this, that if f of x equals a to the x for that a, then the derivative at 0 is exactly 1. It's between 2.7 and 2.72. This number is very special. We call it e. Okay? So this is actually a valid definition of e. E is the number such that if we set f of x equal a to the x, then f prime of 0 equals 1. This has the really nice implication that f of 0 equals 1, right? A to the anything to the 0 equals 1. And f prime of x is equal to f of x. Not times some weird constant, just the function is equal to its derivative. Okay, so this is actually a way of defining e to the x. It's the function that satisfies this equation. This is called a differential equation, an equation involving a function and its derivative. So e to the x is defined to be the function that satisfies this differential equation. Really, we think of it as it's the best base, because if f of x equals e to the x, then the function is its own derivative. So this is like the easiest function ever to differentiate. What's the fifth derivative of e to the x? Oh, it's e to the x. It's just the best thing ever. This also tells us e is approximately, well, it was between, if we look at our last slide, it's somewhere in this interval, right? And you can approximate as much as you want. It turns out e is approximately 2.718. Okay? So there's lots of nice things we can say about e. We don't have time to say them all because it would fill days and days and days. I will say this. There are lots of ways of defining e. This is one of them. This is a good calculus way of defining it. You can certainly define it with other limits as well. You can define it using infinite series, which is my favorite way. But this is going to be our definition, okay? It's this number, approximately 2.718, and e to the x prime is just equal to e to the x again. It is its own derivative. What that says is that as x gets bigger, the slope gets bigger. Okay? Okay, so we're almost done differentiating a to the x. Turns out that if we look at the inverse of e to the x, we get natural log of x, and that's how we get this constant. So for any a greater than 0, if f of x equals a to the x, then if you want to differentiate this, it's supposed to be some constant times a to the x, right? That constant happens to be the natural log of a. Okay, so we can't prove this yet. We will prove it in a couple weeks when we know about the chain rule. But right now, you're just going to have to believe me. We don't use it very much because, like I said, the best base is e to the x. That's the one we almost always use. But just in case you're doing math, like science or something, you want base 10 or whatever, this is the formula for differentiating an exponential. Okay, so with that, I think we'll be done, and I will see you in class.